Hello, everyone. I want to thank you all for joining us today for our ALS Webinar Wednesday series. My name is Kelly Hall, and I'm a marketing coordinator for ALS North America. Our presenter today is Michael Holloway. Michael holds his BS degree in chemistry, a BA in philosophy, and a Master of Science in engineering. He has over 30 years of experience in research and development, technical marketing, equipment reliability and sales, along with publishing numerous books on these subjects. Michael is a certified lubrication specialist, an oil monitoring analyst through STLE, a level 1 and 2 machinery lubrication technician, and a machinery lubrication analyst through ICML. Now, Michael serves as a principal consultant and a certified reliability leader for ALS tribology. Today, Michael will be discussing the impacts and solutions for diesel fuel quality and performance. During this presentation, feel free to use your chat box, ask a question, or raise your hand feature to ask questions. All questions will be answered at the end of Michael's presentation. Michael, thank you for taking the time to deliver this presentation today. I will go ahead and turn it over to you.
Great, thank you very much. I appreciate it. Just to let you know, this is how the webinar is going to be structured. A slight introduction. We go into the classification and properties of fuel, some fuel tests that are performed and their significance, some fuel-related symptoms that you may experience, even some proper fuel sampling techniques, how to read an analysis report, and then if we have time, we'll review with some questions. Now, the question is, why test our fuel? Well, fuel can be contaminated. It can actually deteriorate, and in some cases, the quality of fuel can be actually compromised, either at the distribution site, at the rack, or at your storage facility. The monitoring of which can actually lead to many dollars saved. The objectives of a fuel analysis program, well, one thing is to verify the fuel meets the standards, the performance standards that are going to be required for your assets. We always want to monitor the fuel cleanliness, and that could be anywhere from water, perhaps a different type of fuel, or even bacteria. We want to identify various contaminants that could possibly be the source. We want to monitor the effects of these long-term storage conditions and investigate any operability issues. And finally, we can actually trace back certain asset failures back to the fuel if it's at all possible. Here are some sources of failure and contamination. Everything from the imported oil all the way to the refinery, pipeline storage, distribution, on through to the tankers, and then on through to your storage facility. The fuel can be touched anywhere from 7 to 15 times, all leading to opportunity for failure. More than 85% of fuel systems failure caused by water and dirt in the fuel. Now, water is probably the most ubiquitous contaminant out there. Water can actually occur through the condensation by temperature changes, both above ground and underground tanks. And this moisture can lead to rust and the formation of various voids in between the fuel level and the tank surface. The seepage through filler caps occurs through breather points and even faulty seals. Sometimes cracked pipework can actually lead to water contamination to the fuel storage. There are 3 basic types of contaminants that are found in fuel tanks, and water we just discussed, but also inorganic debris such as sand, rust, dust, metallic particles from tank surfaces, and then the organic debris. Well, that could be sludge and asphaltenes, even polymers and wax. And these things can be actually coming from the fuel itself, but also fungi and bacteria contamination. It's estimated that more than 50% of tank contamination is generally organic. And some say that up to 75% of that could actually be bacteria and fungus that can actually affect and influence the fuel quality. Now, aside from external contamination, filters can be clogged by fuel breakdown products as well. From the time the fuel actually leaves the refinery to the time it's stored, it passes through pipelines and distribution channels. It can be heated. As the fuel actually heats, it actually begins an oxidation process. In high temperatures, oxidation reacts with hydrocarbon molecules in the fuel, and that can cause particulates and gum and discoloration. Low temperatures can actually lead to wax formation due to crystallization, and that can actually plug filters. Now we're going to do some classifications and properties of fuel. Here's a list of the ASTM D975. List out the various types of tests from flashpoint all the way to conductivity and other test methods. Now there's for number 1 diesel, and that's typically for winter use. Number 2 diesel, found throughout the world, and that's probably the most popular diesel. And then there's number 4, and the units measure off to the far right. Number 4 diesels, obviously, as you can see through the viscosity, it's definitely more viscous, used in larger diesel engines. It has a higher ash content. Sometimes valves actually require higher ash content for proper seating. Now, the ASTM 975 standard for diesel fuel specifies the following for most grades. It's the light middle, which is considered the number 1, and the number 2 is the most common. The number 4 is what we talked about with the marine use. This specification allows up to 5% of biodiesel, and that doesn't even have to be labeled. It's provided that the blended fuel still meets its requirements as outlined within that specification. The ASTM 7467 standard spec for diesel fuel and biodiesel specifies that blends of middle distillate all the way up to biodiesel B100. So that would be 100% biodiesel. Now, biodiesel is different than diesel. Biodiesel is a methyl ester, fatty acid methyl ester. It's typically derived from plant. And you can do it from animal, but essentially what happens is we take that particular fat, react it with sodium hydroxide, and pass it through a saponification process and decant off the methyl ester. Upon compression, it'll explode just like a diesel fuel will. Now, these blends are referenced by the amount of biodiesel content in them, which is stated by the B, followed by 2 numbers, anywhere from 101 all the way up to 100. Now, 3 numbers if it's 100. And that's the concentration of biodiesel within the blend. And how this is made, it's a transfer esterification process. You take the animal fat or vegetable fat, for that matter, mix it with an alcohol, typically methanol. You can do ethanol, but methanol is a cheaper alcohol. And put in some sodium hydroxide, 3%, also known as lye or caustic soda. And mix all these ingredients together in a container, leave it to rest, and the chemical reaction goes under typically about an hour. This can be heated up for a fast reaction as well. Now, after that chemical reaction takes place, the products are separated according to their specific weight. You find 2 different layers. The glycerin layer is the heaviest. It'll settle to the bottom. That gets decanted off. And typically that's sent over to a pharmaceutical plant or a cosmetics facility for further processing as a raw material. The other half is the methyl ester. Now, this is the basic method. Other processes are required to enhance the quality as well. There's some tests that are actually performed to get a good understanding of this. One of the most popular tests performed is a cetane number. Now, the time period between the start of the injection and the actual ignition of the fuel, the higher the number, the shorter the delay interval. That's our cetane number. So it's really the speed of ignition. Sometimes people equate cetane as the opposite of octane. Well, octane is, you can test an octane rating in diesel fuel, just like you can test a cetane rating in gasoline if you wanted to. But really, cetane is the quickness of the burn, whereas octane is more of a level of the burn or the consistency of the burn. Now, if we have a low cetane number, that can result in poor cold starting, maybe some excessive smoke, rough running. Typically, according to the engine manufacturer specifications out there, a minimum of 40 cetane for number 1 and number 2 is specified. Although the higher the cetane number, obviously the better quality, better performance of the fuel. Biodiesels have been known to have cetanes in the order of up to 60. Now, the cetane number requires burning the fuel in a special diesel engine called a cooperative fuel research engine. There's not that many labs that have these engines. They're actually quite expensive to run. But it does run from a scale from 0 to 100 based upon a rating of reference materials. In lieu of the fact that these engines are actually difficult to operate and difficult to run and expensive, we can also use a cetane index instead. Now, cetane index is used to estimate the natural cetane number of diesel fuel. It's not affected by cetane number improvers per se. It's an algorithm that uses the API gravity and distillation to determine the estimated cetane number. Another important test to run on fuel is the viscosity. Low viscosity increases the potential for fuel injection pump and injector leakage, which can lead to power loss. The fuel has to meet a certain viscosity specification. So the correct viscosity allows for the fuel to properly atomize and lubricate. This has a direct impact on emissions as well. The better the atomization, the better the burn, the more thorough the burn, the less soot and the less hydrocarbons that may actually escape through the emission system. Viscosity can alter the fuel delivery metering as well. The specifications for number 1 is between 1.3 and 2.4 centistokes. Number 2 is between 1.9 and 4.1 centistokes. And this is typically done through kinematic viscosity, much the same way in which we test the viscosity for lubricating oil. Distillation is also run. This measures the volatility and performance of the fuel. And it can indicate contamination as well. This gives a nice spread of the light, the fines, all the way up to the heavy residuals. There's the specification for number 1 and number 2, 90% recorded at 288. We have to have 90% recorded at 338 degrees for number 2. There's also ash content. And ash is actually the metallic residue left behind combustion. It's abrasive particles that can actually contribute to wear and deposits. These soluble metallic soaps contribute to engine deposits. In certain cases, for instance, in natural gas engines, a certain ash requirement may be needed for valve seating. But typically in a diesel engine, the lower the ash, the better the performance. The number 1 diesel specification is 0.01 maximum ash, as it is with number 2. Here, material is actually put in a flash cup and burned until we have the metallic residue left behind and weighed. There's also a carbon residue test, and that measures the coking tendency, the approximation engine deposit potential as well, very similar to the ash content. But here we're actually not looking particularly at the metallic residue, we're looking at the carbon coke left behind. In this case, the number 2 diesel spec is 0.35%. We're also going to explore the sulfur content. Now, back in 2007, ultra-low sulfur diesel fuel specification was employed where we couldn't have more than 15 parts per million sulfur in diesel fuel for over the road. Now, the sulfur content can be measured using a UV spectroscopy. This reduced sulfur content decreases the sulfuric acid production and combustion process. Once again, the specification was put in place for emissions. It's EPA regulated. It's also been known that high sulfur fuel can actually deplete the alkalinity reserve in engine oils. It brings about a higher content of sulfuric acids that can actually form within the oil, promoting oxidation. In some cases, it's been believed that it'll actually promote corrosion. There's also flash point. Now, flash point is the lowest temperature at which the ignition causes vapors to ignite. And that can indicate contamination by maybe a lighter or a heavier grade fuel for that matter. For number 2 diesel specification, 52 degrees centigrade is the minimum flash point. If we have a heavier constituent in there, then obviously that flash point is going to be higher. If there's gasoline or a low boiling solvent of sorts, then we could actually have a lower flash point. That can be a bit of an issue as well. One thing we always want to keep an eye on is the amount of water we have in our system. The less water, the better, obviously. The KARL FISCHER is actually one test that performs quite well at understanding all the way down to a couple parts per million as to how much water would be in our system. It's a precise method to determine water content. It's an iodine water reaction through electrolysis and a type of titration mechanism. The reaction is actually added until electromagnetic endpoint is reached. The water concentration or percent is calculated from the amount of reagent used to reach a particular endpoint. Now, number 2 diesel specification is up to 200 parts per million maximum. Water is actually going to influence the combustion process, but it's also going to promote biological growth. Here's a picture of a KARL FISCHER titrator. Here we can take a look at the fuel cleanliness on the D2276, where we can actually filter out and understand the particular contamination by weight. This type of a filter can actually be examined under a microscope to get a better understanding of the actual contaminants that are precipitating out. There's also various ways to understand the microbial growth in diesel fuel. The most common symptoms associated with microbial growth contamination are plugged filters and corrosion. As bacteria and certain fungus actually live, they give off a corrosive byproduct. Even after treatment of the biocide, problems can still persist and a fuel system is not cleaned and waste byproduct with excessive water contamination isn't removed. Often a biocide is used, but you have to be careful when you use a biocide. If you put a biocide in a fuel tank continuously, at some point, these bugs could actually become resistant to the biocide. Another thing to consider too is once you add your biocide in a full tank and mitigate and kill all the bacteria and fungus that may be in there, that tank has to be completely emptied before a new load of fuel is incorporated. You see, if you incorporate more fuel on top of a biocide, it'll dilute down that biocide. The problem with that is that a diluted biocide can actually promote biological growth. This is analogous to how certain nefarious racehorse owners would actually give a little bit of cyanide to the racehorses to boost their metabolism. Not enough cyanide to actually kill them, but it's enough cyanide to boost the metabolism. And the same thing happens with a biocide in the bacterial growth medium. It's unfortunate, but a lot of times we want to be able to kill and mitigate these biologicals. But the problem is that in the good faith that we're trying to achieve, sometimes we don't consider the actual mechanism at play here. Another thing to consider too is the corrosivity of the diesel fuel. We want to understand the corrosive potential, and here we're actually going to expose diesel fuel to various copper strips and then let it sit for a period of time, and then examine the copper strips afterwards for a tarnish layer. The specification for diesel fuel is a 3B. API gravity also an important consideration of diesel fuel. This should be tested as well. Gravity is an excellent indicator of contamination. The measure of gravity is quite easy to obtain and generally correlates with the energy content as well. The specification for diesel fuel is 39 maximum for number 2. Now here's a correlation between the API gravity versus specific gravity. You can see they're inverse, if you will. As the specific gravity decreases, the API gravity increases. So API gravity is actually, as API gravity number increases, the weight pound per US gallon will decrease. One thing to consider is the lubricity of a diesel fuel. With the advent of using biodiesel, let's improve the lubricity. That's a good thing because when we went to ULSD, the ultra-low sulfur diesel fuel, well, the sulfur is removed, but also removed a lot of natural lubrication that diesel fuel had. And actually, the amount of injectors that were used after that change increased by several fold, unfortunately. And that meant there was a lot of injector wear due to lack of lubricity of the fuel. There are lubricity additives that can be bought on the market, and they improve, and also biodiesel can actually improve lubricity as well. We want to get an understanding of lubricity of the fuel so the fuel injectors can actually work properly. Now, the fuel functions as a lubricant in most components of the fuel injection system, not only the injectors, but also the pumps and throughout. The poor lubricity is important to reduce the wear of fuel injection equipment. If you have worn injectors, you're going to have a potential for pre or post detonation, which can be very deleterious on a combustion chamber. But also, we're going to have a reduced power, and we're also probably going to have problems with the emissions as well. Here's actually how we can test the lubricity. HFRR stands for High Frequency Reciprocating Rig. It's an instrument that can actually understand the lubricity of fuel, and it measures a wear scar in a steel bar after the prescribed test conditions. One other thing to keep in mind is the acid number. Now, we perform acid number on a number of industrial lubricants, in some cases even diesel engine oil. But acid number is performed on diesel fuel. It's traditionally used to measure the acidic constituents of fuel and for the corrosion potential. Here we can look at the concentration, but not necessarily the particular acids that are forming. For a particular acid that are forming, sometimes we can actually take a look at the overall graph of the total acid number and discern from that, or run an IPH. But in this case, we're actually looking at the concentration acid as it builds over time. They can be used to measure the level of fatty acids present in the biodiesel and biodiesel blends as well. Now, with the inclusion of the biodiesel into the market, we have a rise in need to measure the acid content. The specification for a number 2 or number 1 is a 0.15 milligrams per KOH per gram sample, and that's the max. We can also keep an eye on the bio blend, and this is an important feature as fuel is delivered to us to make sure that's within specification and what we're looking to buy. Often there, depending upon the state of the company, there might be certain mandates that we do want to use a bio blend or 100% bio, but we want to make sure that is in check. Here we actually use FTIR to measure the ester peak, not present in conventional distillate fuels. One other test that's run is oxidation stability. Now, this is specific to a B100 and biodiesel blends. It's not a requirement in the D975. This is used to measure the oxidation byproducts that can cause fuel system deposits and filter plugging. If you think that we've had filter plugging due to fuel, there's one test that actually can be run. This takes approximately 6 hours. We're going to look at long-term storage. We want to understand if the fuel is actually suitable for use after it's been in the system for a while. This comes in handy for understanding if the fuel in a standby generator is still effective, or if it actually has to be changed out. Last thing you want to do is then have a standby generator go down when you need it, and it's due to a fuel problem. Now, in general, diesel fuels have adequate storage stability for normal use. As temperatures increase, though, the oxidation increases within the fuel, and the cetane number can actually drop and can have other problems. If storage is going to be for more than 12 months, testing the fuel before is actually recommended. Your periodic analysis will improve the means to make important decisions regarding aged fuel, its storage and suitability for continued use. There are additives on the market which you can add to your fuel for increased storage life as well. Now, most modern fuel systems are designed to return the non-injected portion into the fuel tank. This return fuel has been highly pressurized and heated, which promotes polymerization in certain cases, which is actually the oxidation and the breakdown of fuel, creating some carbon particulate. As more fuel is pressurized and heated and recirculated, the amount of this carbon particulate generated in the system increases, leading to possible injector failure and filter plugging. We have low temperature effects on fuel as well. We may not experience this in certain states like maybe in New Mexico, Arizona throughout the year, but in the northern states, stabilized paraffins that can actually precipitate out in cold temps and form wax crystals. And this crystallization could contribute to filter plugging and actually starve the fuel of the engine. And with enough wax formation, the fuel will gel and not be able to be pumped. This has been a big problem as well with biodiesel, especially if biodiesel is processed with animal fat that can solidify between 25 and 35 degrees Fahrenheit. We'll want to check for the cloud point. Here's a test that can be run. In this test, the temperature at which the first formation or the wax cloud begins to occur. The highest temperature of low temperature operability issues may actually occur here. In this case, the typical is 10 degrees. There are no specifications for this, but if you are running in a colder environment, it might be a good internal specification to establish. Along with the cloud point is a pour point, and that's the lowest temperature before the fuel becomes a solid. Now, these specifications can vary according to the climate conditions, but typically it solidifies at minus 10 degrees Fahrenheit for a normal number 2 diesel fuel. Once again, there are additives that can be bought on market to lower the pour point and cloud point of diesel fuels. The last one is a cold filter plug point, and that's the temperature at which 20 milliliters of fuel will not pass through a 45 micron wire mesh within 60 seconds under vacuum. That's the test conditions. Once again, these are geographically and seasonally dependent. There's various fuel-related problems throughout your system, be it clogged fuel injectors, damaged fuel pumps, blocked fuel filters, water getting in there and forming sludge in the oil, as well as engine deposits, and even bacterial growth. And yes, bacterial growth can occur in an engine, albeit hot, there are still places which bacteria can grow and create more problems. Bacteria growth can actually occur in other types of lubricated systems as well, but it is found in fuel-related systems within your engines. Here's an example of the common rail system, the Tier 4s that are currently on the market, with their electronically controlled injectors and the common rail for the fuel distribution. And these do have a high pressure tube connector. These things are very susceptible to contamination. The clearance in these supply pumps and injectors have an accuracy of limits of micron size and fuel injection pressure up to 22,000 psi. An invasion of water and dust into that fuel line must be controlled strictly compared to the conventional fuel systems. And now accordingly, a pre-fuel filter of 10 microns with a water separator is mandated, and a main fuel filter of a 2 micron absolute is installed in those high pressure systems. And we're talking about some very tight tolerances. When we talk about a micron, obviously a human hair can be anywhere between 75 maybe to 110 microns. Human beings can only see not much below 40 microns. Give you an idea of some of the various things that actually are out there, but rust inhibitors might be below a micron, some bacteria between 1 to 3 microns. But if you look at the tolerances here, or we look at the filter media, the match clearances, even the spray hole diameters, these small particulates can actually have a huge impact on the overall opportunity for failure in an engine. It's real important that the fuel filters are up to date and maintained, making sure that they're changed out periodically if we are starting to see a compromise in pressure or a compromise in an increase in particulate. Now here's a graph that shows the effect of water on injector life. And this is taken from a Commons report published several years ago at an SAE conference. Now the injector life percentage, if we look at just basically at 100, we can see where the amount of water has a huge influence on the injector life itself. And this is in parts per million. We can extend out the injector life by 2.5-fold just by decreasing the amount of water we have in our injectors, or in our fuel. Here's just an example of a diagram of an injector. Here's a picture of injector wear. Worn out seat, worn out nozzle seat. And these are typically due to dust on the kind of data that we're going to be looking at. Our sample has to be representative, and that means that the opportunity for any kind of cross-contamination has to be eliminated. In our sample, we could look for dirt, dust, fuel degradation material, even water, maybe a wrong product or processed materials as well. And that's an important understanding, but if we contaminate the sample through an outside source, then our data becomes meaningless. Now, sample equipment and equipment cleanliness is important. Close containers immediately after the sample is taken. And distillates are generally homogeneous, so it's not to worry about any kind of level, but we do always want to take from the middle of the tank. Now, if you do take from the bottom of the tank to try to grab as much of the garbage as possible, make sure you label that. It's usually a good idea to get a representative sample from the line as well, going straight into the system. And obviously, proper labeling is always important. The more information you can put down on the label, obviously, it's going to aid in the diagnostician's assessment of the sample. Here's some common sampling equipment. As you can see up, the vacuum sampling pump, that's typically used for oil samples. It has been used for fuel samples as well. The weighted container or bacon bomb or even are typically the better choices, where they can actually be lowered down into the storage tank and a sample taken that way. There's also a core tube that can be used too. Now, obviously, you can't use a weighted container or a bacon bomb in an asset over the road or off road. That's where a sampling tube can come in handy, where the sampling pump is. Now, some guidelines to consider. The tank bottom sample is ideal for monitoring tank cleanliness, but poor for measuring the fuel quality. Now, mid and top samples combined to make a composite sample is appropriate for fuel quality analysis. That's a bit of a deviation from taking an oil sample. You want to sample immediately after topping off the fuel tank, and that's ideal. That purports a certain amount of agitation within the fuel tank and giving us the most representative sample. Now, how can you actually go about reading a report? Now, when we first take a look at a report, it may actually seem like a foreign language, but my suggestion is, as soon as you get the report, I'd call up the lab and speak to someone and have them go through it with you. If not, we could go through it right now. You'll notice at the top, the UIN, that stands for Unique Identification Number. Now, those kind of numbers are just for you and the lab only. Okay, the lab uses those numbers as its own personal fingerprint. It's going to have the tank ID, and that's important, as well as the fuel type. Now, you can even put down not only diesel fuel, but if it's a bio blend, or for that matter, if it's number 2 or number 1, that'd be very, very helpful. We want to put down the serial number if appropriate for an asset, and even put down the site where it's located. We want to give an idea of the compartment name, the fuel manufacturer, if it's at all possible, where you're getting the fuel from, and the type. We want to put down the tank capacity. A 10-gallon tank versus a 10,000-gallon tank. Well, if you have 0.1% water in a 10-gallon tank, that means one thing. But if you have 0.1% water in a 10,000-gallon tank, that's a pretty significant contamination. We always want to put down the date sample and the date received and the date reported. That's for 2 reasons. The lab wants to know when you're taking a sample, but it's very important to have you understand when the lab actually receives that sample as well. Sometimes there are special handling procedures for diesel fuel samples. All the labs will actually provide you that information. There are special postage and handling as well as containers that are to be used. All right. We also want to make sure that we understand when the date is reported. It gives you the lab number for reference as well. Now, if we look at the test methods here in this particular, the first thing we look at is the appearance, the distillate fuel appearance. Clear and bright, free of water and particulate. In this case, the results are hazy, excessive free water, and excessive particulate. Next, they ran a distillation on this, with the initial boiling point all the way up to the percent recovered. And then the physical properties, the API gravity, the calculated cetane. Now, once again, many labs can't run a pure cetane number only because they don't have the engines, but they can calculate that with the distillation and the API gravity. And it's within a couple decimal points of being pretty darn accurate as well. The coal filter plug point was established here. Now, as you can see, we have a KARL FISCHER of 1695 parts per million water, and you'll notice that particular value is in bold. That means that's an alarm. That's out of spec. Everything else has been in spec so far until that. We do have a certain sulfur percentage though. It's 18. Now, that actually starts trending up. It's supposed to be under 15, but there might be a reason why that's 18. When we're talking about parts per million, sometimes that could be due to experimental error, could be due to sampling. It might actually be due to the fact that the refinery didn't produce that fuel that was under 15 parts per million. Don't necessarily know. So a value like 18 is something that might be put in question, but not necessarily an alarm yet. You actually see the water by distillation. And when it is water by distillation, that typically is going to be purporting down to the water that's dissolved or entrained in some cases. Some folks call it entrained, other folks use all dissolved. It might be emulsified, but the water by distillation is popping out at 0.3% volume. And then we look at the biodiesel content. It's 1.6% volume. Here is a great example. You can have up to 5% biodiesel. It doesn't necessarily have to be reported. Now, why do some refineries do this? Well, there's a couple reasons. It's all about the amount of taxation that can actually be occurred in some cases. It's an additive. It's a lubricity additive. It can actually help you out in that case. But they're putting up there, and just like they can put up ethanol up to 15% in gasoline and report it as an E10. Here we have an acid number, relatively low, 0.07, and then a cloud point This wasn't analyzed. What was analyzed was the total particulate. So here we have 32 milligrams per liter in a particulate according to the D5452. Now that's out of range as well. So we're looking at not only wet fuel, we're also looking at dirty fuel. This can lead to excessive problems down the line with any kind of asset that this fuel is going to go into. Now here's an example of a fuel that was taken out of a bulk tank. As far as the appearance goes, it passed for appearance, but it did have excessive free water and particulate. So although the fuel may have been clear and bright, it still had free water and particulate in it. But we will notice that overall, the other things that were tested do fall in spec without any alarm limits covered. Here's an example of a marine diesel fuel. In this case, there was trace particulate, free water, it passed, there was no free water, and it was clear and bright. Everything was in line with the distillation, the physical test as well. Now, this is typically a number 4 diesel fuel, so the viscosity is a little, is well within spec. You'll notice also that the sulfur, 363, with this particular specification, has to be under 500 parts per million. You'll see the total particulate is within spec as well as the flash point, and as is the gravity. Very little amount of water and sediment in this particular sample. The calculated cetane here is 50.9, and it's got excellent corrosion, anti-corrosion with an A1. Its ash content is exceptionally low, as well as the Conradson's carbon residue as well. Now we've come to the end of our presentation. We explored the different types of contaminants that can actually influence our fuel. We looked at all different types of test methods and the specifications thereof. We reviewed how to take a good sample, making sure it's representative and timely sent into the lab, and then reviewed the analysis on different types of fuel analysis that were sent into the lab and get a good understanding of what's tested, what the alarms are, and how we can go about going forward. Now I can open this up for questions for the next several minutes.
Yes, thank you, Michael. We will go ahead and open up for questions. Remember, you can use your chat box. You can ask a question in the Ask a Question box, or even use the Raise Your Hand feature and you can ask Michael a question directly. While we wait for these questions to come in, I just wanted to remind everyone today that this webinar presentation has been recorded. All participants of this webinar will receive a follow-up email once the recording is available to view. We do post our webinars on our ALS Global website and our YouTube channel. We do have a question coming in from Alex. The question is, I recently received a colorless DMA sample. Have you ever seen something like this? All tests are within specifications.
Yeah, actually, I guess I probably have seen results where diesel marine fuel has come in, but colorless is a little bit on that. That kind of surprised me somewhat. Normally they do it. It might be on a darker, but as far as colorless goes, what do you mean water white? I've never seen water white diesel fuel, but not to say that there isn't. I mean, there's even such a thing as water white clear crude oil that comes out of the Gulf in certain parts of the world too. So it doesn't surprise me, but normally it would be, it would have a tint to it, either an amber all the way up to being a darker tint. And obviously bunker fuel would be very dark. I've never seen clear, I've never seen it, but it's very possible it's out there. I wonder if anybody within the audience has ever heard of such a thing.
I don't see any additional questions coming in, but just again, as a reminder, we do record these webinars and you will be receiving an email follow-up once the recording is available to view, along with contact information if you did have any follow-up questions for Michael. Alex had a continuation question on that last one. He said, I particularly never got a similar sample, but this time we got it. The unit's own onboard staff looked weird and interrupted the supply.
Yeah, it's very strange. Like I said, I've never, the only clear fuel I've ever witnessed is gasoline, and even then it has a little bit of, to be completely clear, that's really very bizarre. And if it came if it all came back within spec, that's I don't know. That's a good one. Geez, I have no idea. It's very bizarre. I'm gonna have to look into that.
All right, that looks like the last question we have. Again, I want to thank everyone today for attending our Webinar Wednesday series, and hopefully you can enjoy the rest of your week. Thank you very much. Thanks, Michael.
Great, thank you.